Hi folks, welcome back to 5.2. This is part 2 of the videos. So last time we were here, we finished by talking about how we could use area in certain cases to help us shortcut integrals that were maybe really difficult looking. And so what we're going to start with right now is we're going to take a look at a case where maybe area is not as useful. Okay? So if I look at what I have here, I have a definite integral, and I know that because I have a bottom bound or starting point at 0 and a top bound at 1 or an ending point at 1. And I have this function here, 1 minus x squared. Now this squared tells me that I have a parabola going in here, and parabolas are not nice geometric shapes, in the sense that I don't have an area formula for a parabola like I do with a triangle or a circle or a rectangle or a trapezoid, okay? So having gone through that reasoning, what I'm going to do now is see if I can use antiderivatives to solve this. So here's where we're going to start. We're going to take their integral from 0 to 1. But I'm going to write out 1 minus x squared as 1 minus x times 1 minus x dx. And now I'm going to go ahead and FOIL that. And so that is going to give me the integral from 0 to 1 of 1 minus 2x plus x squared dx. Okay? Now what I'm going to do is I'm going to find the antiderivative of each part. So where did 1 come from? Well, 1 came from x. Minus, what did I take a derivative of to get 2x? And that comes from x squared. And what did I take a derivative of to get x squared? And that is 1/3 x cubed. Now again, I'm not going to have a plus c, but I'm going to draw a bar. I'm going to put a 1 at the top because that's my top bound, and a 0 at the bottom because that's my bottom bound. All right, so let's bring our problem up here for us to plug in our numbers. So I'm going to get 1 minus 1 squared plus 1/3 times 1 cubed minus 0 minus 0 squared plus 1/3 times 0 cubed. Okay. So if I simplify this, I will get 1 minus 1 plus 1/3 minus 0 because this whole thing goes to 0. And so 1 minus 1 is also 0, and I end up with a final area of 1/3. So again, sometimes it's easier to take the antiderivative, and sometimes it's easier to find the area using geometry. Okay, so let's move on. We're going to talk about two concepts here called net area and total area. All right, so when we have net area, all right, that's what we're going to talk about first. And with net area, signs matter. Okay, so signs matter. However, when we get to total area, we're going to be looking at a case where we're going to assume that everything is positive, okay? So let's look at the net area first. So I've got this graph right here. This graph represents x minus 2, and we're starting at 0 and we're ending at 6. Okay, so I'm going to be starting at x equals 0, and I'm going to be ending at x equals 6. And when I look at that, I see two triangles. I see one down here, and that one for net area is going to be negative because it's below the x-axis and we're going this way. And then I have this area up here, which is going to be positive because it's above the x-axis and I'm going from left to right, okay? So let's go ahead and find our net area using geometry. So I've got the first area is going to be negative 1/2. The base is 2. The height is 2. Plus the second area is 1/2. The base is 4. The height is 4. So this is area 1, and this one is area 2. And when we calculate that out, we will get -2 plus 8, which will give us a net area of 6. Now, because this is a pretty straightforward question, I want us to try and do this using antiderivatives as well, just to get that practice in. So, integral from 0 to 6 of x minus 2 dx. Okay, so where did x come from? It came from 1/2 x squared. Minus, where did 2 come from? It came from 2x. I'm going to draw a bar. I'm going to put the 6 at the top and a 0 at the bottom. So I will get 1/2 6 squared minus 2 times 6 minus 1/2 0 squared minus 2 times 0. And that will give me 18 minus 12 or minus 0, and that will give me a a net area of 6, okay? So we did this net area 2 different ways, and we got the same answer, which is good because we should get the same answer regardless of which method we choose. So let's see what's so different about this total area. So total area, we are going to consider this like an absolute value case, okay? An absolute value means that if it's positive, but if it's negative, it's also positive, because we're just looking to see how much area is there altogether, okay? So if we want to use our graph, then we actually need to almost redraw our graph a little bit. So this part is going to stay, okay, because that's already above the x-axis. But the part that's below, I'm going to reflect that, and so I really end up with something that looks like an absolute value graph. And I have the same starting point, and I have the same ending point. Now with total area, you can do this one of 2 ways, okay? So I think that geometry tends to be easier for total area. So I'm going to say I want to find the area of the first part, and I'm going to add that to the area of the second part. So the area of the first part is 1/2 2 times 2, plus the area of the second half is 1/2 4 times 4. And so instead of subtracting 1 this time, I end up with 2 plus 8, which gives me a total area of 10. Okay? Now, if you want to set up your definite integral, this is what you would have to do. The integral from 0 to 6 of the absolute value of x minus 2 dx. Now, those absolute value bars take care of the fact that it's total area, okay? But these are integrals that we don't really know how to do yet, so for the total area, I would advise using geometry. Okay, let's take a look at one more question on net versus total area. So, example number 5. Find the net and total area for, that's supposed to say area, for this integral from -3 to 3 of 2x. So I'm going to go ahead and sketch a quick graph. All right, 2x looks something like this. All right, it goes to the origin, it has a slope of 2. And so let's get where our starting point is at -3. So -3, I'm going to drop down that perpendicular. This point is -3, -6. And then where am I stopping? I'm stopping at 3, so that's like here, and this is 3, 6. Now, one of the things that you can do is if you know that 2 different areas are exactly the same size. So for example, I know that this area 1 is exactly the same size as area 2 because these coordinates are just reflections of each other. So if 1 is positive and 1 is negative, then I can say that the net area is going to be 0. Okay? Now, if I wanted to set up the definite integral, let's see if we get the same answer. So the integral from -3 to 3 of 2x dx equals, where did 2x come from? It came from x squared. I'm going to plug in 3 and -3, and I get 9 minus 9, which is 0. Okay. So sometimes you are going to get 0 out, and that is totally fine, okay? Totally fine. But what that means is that the areas balance each other out, all right? One is positive, the other is negative. Well, let's take a look at our total area. If I wanted the total area, I could draw this part of the graph. That part would stay the same, and I could say that that ending point is 3, 6. But I would have to take the bottom triangle and flip that up so it was some sort of absolute value. And I'm going to drop the line down like this, and that is going to also be -3, +6. Okay. Well, if I want to find the total area, then I have the area 1 plus area 2. All right, so I've got 1 here and 2 here. So 1/2 base is 3, height is 6, plus 1/2 base is 3, height is 6. And so that's going to give me 9 plus 9, or 18, as my total area. Okay? So again, sometimes you can have a net area of 0, that's okay, but the total area won't always be 0. Sometimes it'll be twice what one of those values was, especially if they're balanced out. Okay? So we're going to stop here for part 2 of the video. Come on back for part 3, and I'll see you there.